Welcome back to my ongoing lecture series about physical chemistry. This is the last part of chapter 6, looking at Gibbs, chemical potential, and finally now we're going to bring in chemical equilibrium, the idea of how spontaneity reflects the equilibrium expression K that we know from general chemistry. Okay, so let's look at this. Last left off, we were talking all about chemical potential. So now we're looking at a reaction where A and B go to form C and D. Would write the equation where alpha and beta and gamma and delta are coefficients. Let's go alpha A plus beta B yields gamma C and delta D. And that we'd have to remember that we defined the absolute Gibbs, change for the absolute Gibbs was equal to the sum of the chemical potential of each component times the number of moles of each component, the change in the moles of each component. So we're about to introduce a new variable, xi. It looks almost like a squiggly E. But xi is a way of picturing the extent of a reaction. So how far has the reaction progressed? If we say xi is equal to 0, then no reaction has taken place. The reaction has not begun. We say xi is 1, the reaction has occurred one full time, one full turnover of that reaction. Kind of like a mole fraction, like how far has the reaction progressed? If the reaction is 1 mole of this goes to 1 mole of that, then when 1 mole has been consumed, xi would equal 1. If half a mole was consumed, then xi would be 1/2. If 3 moles have been consumed, xi would be 3. So such to the point where we can essentially say that the moles of a reactant at time t will be the moles initially plus our nu, which we use to say the coefficient times xi at time t. So, for example, if 1 mole is consumed, it would be -1 times xi, however many times the reaction has gone. If it's gone 5 times, it would be 5 times -1 to figure out how much moles have been consumed. So in general, the change in moles would be equal to nu delta psi. So how does psi change? Changing psi with the coefficient. So with that in mind, we can now exchange our changing Gibbs is equal to the sum of potential times changing moles into the sum of the coefficient nu for the chemical reaction times the chemical potential of that species times changing psi, so how much of the reaction has gone. And we can actually divide by xi, changing xi. So how does Gibbs change with changing chemical reaction is equal to the sum of the coefficients times the chemical potential, or essentially delta G for a reaction. So that's the sum of the chemical potential of all things times the coefficients, that is delta G. Now, because that the delta G of reaction is equal to the sum of the coefficients times the Gibbs mole enthalpy, that we can set those equal. But so what does this term actually mean? What does dg over dxi actually stand for? It's saying, how does the Gibbs energy, which Gibbs energy is a way of modeling the spontaneity or even the maximum work potential that we can get out, how does this spontaneity, this work potential, this whatever change as the reaction goes forward? So if the Gibbs energy is less than 0, to be negative, as xi is going forward, the reaction is spontaneously proceeding towards products. If Gibbs is going negative as xi is going up, then it's going to keep producing products. If Gibbs is going more positive as it's continuing, this is a non-spontaneous system. And so this is actually going to go spontaneous in the other way. And of course, if Gibbs is not changing as the reaction is proceeding, then the reaction is at equilibrium. There is no direction that results in spontaneous change. In math terms, if G is at a minimum, we're at equilibrium. Now, the goal of this reaction is to get the greatest delta G M for that reaction. The absolute delta G. Let's look at a standard reaction where 2 NO2s goes to N2O4. The moles of reaction at any point in this reaction is going to be 2 minus 2 xi for NO2 and just xi for N2O4. So 0 plus xi as it progresses. While this may look weird, it's essentially 2 minus 2x and x, just like a standard ICE table would say ICE. I of NO2 is 2. I of N2O4 before the reaction has begun is 0. We subtract 2x as the change in NO2 and add 1x to the change in N2O4. At equilibrium, we're going to be 2 minus 2x and x. So at the start of the reaction, xi is 0. The reaction is complete when xi is equal to 1, because then we'd have consumed all of our NO2. Move my face out of the way. But right here, so looking at this, so this is just thinking about delta G pure. That on a pure sample, we're going to go from reaction progresses till we get the lowest possible delta G when xi is equal to 1. In a perfect world where everything's kept separately, it's going to be linear, just straight down. As this progresses, this is being consumed, and we're going to produce greater spontaneity as that goes forward. So, but that's only if we're looking at pure delta G values. So they're saying that, oh, if there's more spontaneity in this product, then we're going to form more of this product, and then it's going to keep going and keep going and keep going until all of the reaction is consumed and all the product is formed. So if this was true, then if delta G in equilibrium only depended on the pure values, then all reactions would either not go or go to 100% completion, just by looking at what is the absolute Gibbs energy of products and reactants. But delta G of a reaction is dependent on the mixing as well. So we have to consider the pure delta Gs, but also the effect of what is the entropy of mixing. So as you're adding the delta G of mixing, which was, remember that from last talk, was RT ln what chi ln chi, nRT sum of ln chi of chi ln chi. There's going to be a point where that RT chi ln nRT chi ln chi is going to be at a maximum addition. So you're going to get a local minima that's not quite at 0 or 100. So this effect is going to result in what amount of products would we have. So the minima doesn't necessarily lie on either extreme. So in case of Gibbs-M, if the reactants and products are in similar size, then the delta G mixing will determine the reaction's extent largely. So if products and reactants have similar delta Gs, then the mixing will have a large impact. But if delta G of reactants and products are widely different in size, then mixing will play very little part. Reaction will actually resemble a pure product or pure reactant. So for example, we know acetic acid is a weak acid. Acetic acid does not largely dissociate. It does dissociate, but it doesn't do it a lot. So what does that tell us? Is that, well, that mixing plays some sort of part. It's not going to go forward. It's very much. But we know strong HCl is a strong acid, and that almost always completely dissociates in water. So the effect of mixing does not really affect the yield. It's considered essentially 100%. So the easiest way to calculate this is if we look at the delta G reaction, we're going to say the sum of the molar quantities times the Gibbs of formation for each individual thing. So here's our first example of this. So what would the delta G reaction be for 2NO2 goes to N2O4 at 298 and 400 Kelvin? So we got to look at what is our Gibbs formation of each of these guys. We can look those up. Pretty straightforward. So look up that Gibbs formation of N2O4 is 99.8. Gibbs formation of NO2 is 51.3. Say the delta G for this reaction is negative 2.8. Calculating this again at 400 Kelvin, we have to look up our delta H of reaction, of course. Delta H reaction is negative 55.3. So we have negative 55.3 times 1 over 400 minus 1 over 298. And that's going to have effect of, well, that's a positive 0.047. We're going to add that to negative 2.8 over 298. That's going to result in positive 0.037. And at 400, it's actually 15.13. So the delta G of the reaction is now non-spontaneous at 400 Kelvin. Non-spontaneous by a lot. Now, what about delta G reactions for gases outside their standard state? So let's look at this again. So it's no longer at 1 atmosphere. We're looking at how does the pressure change. So we have to add in the effect of the pressures. So delta G reaction, we have to look at the change in these guys. So the pressure, now that we're allowing pressure to change, we still have that negative 2.8. looking at this, so that's 1 atmosphere of that and 2 atmospheres of that effect. So we're saying, oh, okay, so, and we're adding the RT pressure of N2O4 minus pressure of NO2. Simplify this. So we can take these two terms and put them together. That pressure of this and pressure of that. When you take the natural log and subtract another natural log, and that you can pull those 2's in there. You have 2 squared and 1. So pressure over pressure. And this was what we had before. This was our delta G reaction. So delta G reaction at a temperature and pressure is delta G reaction standard plus RT ln pressure of each individual gas raised to the power of their exponents. Now, this might look semi-familiar, except for those P naughts. This looks semi-familiar. Why should this look familiar? Well, this is our QP, our reaction quotient from general chemistry. That for a reaction, you could write a reaction quotient expression of products over reactants raised to the power of their coefficients. And you could do, if it's QP, we're looking at pressures. We're looking at QC, which we'll talk about in a minute, it's looking at concentrations. But let's look at it. How does this differ from what we've seen in the past is that everything is raised over P naught. But what is P naught? P naught is 1 bar, the standard pressure. So what will that essentially do? If we divide everything by 1 bar, it will cancel out the units. It's just there to cancel out the units. Now, if you recall back to any time in general chemistry, you may recall that Q and K never had units. The reason behind this has to do with this P naught. Canceling out bar over bar cancels the pressure, or atmosphere over atmosphere cancels the pressure. So, and this should look like a familiar equation from general chemistry. Delta G equals delta G naught RT ln Q. That when we add RT ln Q, we're essentially calculating what is the Gibbs reaction as the reaction has progressed. If the pressure of these gases has gone up and the pressure of these gases have gone down, essentially, the Gibbs is going to become more positive or less negative. Now, remember, QP is the reaction quotient. We've seen this before. So, I'm jumping ahead without reading my slide, but that's okay. Essentially, we've seen this reaction before. This reaction is everything we've learned at the very tail end of our second semester general chemistry. So in this way, it's another way of factoring out how the reaction will progress. What is the spontaneity of reaction as it is progressing? If we have a large QP, spontaneity will decrease. If we have a small QP, so less than 1, spontaneity will increase. Now, the point where delta G reaction is 0 becomes a special case when delta G reaction is delta G naught of reaction is equal to negative RT ln Q. So when those two terms are equal and they cancel out, this is known as equilibrium. So Kp or ln is this equilibrium, reaction quotient at equilibrium. So ln Kp is said to be equal to negative delta G naught over RT. We essentially exchange Kp for Q and got ln Kp by itself. Okay. Now looking at how does Kp vary with temperature? So we all talked about the only way to change an equilibrium constant was to vary the temperature. So how can we do that? How can we do that? So we're going to do that with a little bit of math. We're going to look at, we just saw that statement that ln Kp equals negative delta G over RT. So let's see, how does ln Kp change with temperature? Well, we can say that's equal to, how does delta of delta G over RT change with temperature? Factoring out the constant, which is R, we have delta G over T over dt. And remember, we found that one. In our proof, the Gibbs-Helmholtz relationship, we said that, oh, delta, how does G E over T change with changing T? That was equal to negative H over RT over T squared. So factoring that negative H over T squared times the negative 1 over R says, okay, right, the natural log of K varies with T as a function of H over T squared. So if we integrate these two things, so we get the dt to the other side and integrate both sides, with temperature, we get that, okay, natural log Kp is equal to the natural log at 298 minus, so we have 1 over T squared, and we integrate that becomes negative 1 over T. So integrate that, so you take out the negative H over R, those are constant, 1 over T minus 1 over 298. So this is kind of similar to that delta G version. So we still have to find K at 298. And we still have to find delta H reaction. Sorry. What the heck? Okay. We still have to find delta H at 298 and K at 298, but if we do that, we can find K at any temperature. Now, that works for most things. Now, Kp of solids and Kp of liquids. If you remember, why we never included solids and liquids into K expressions. We're finally going to get to that. It took us a couple years, but we're finally getting around to this. Well, remember, Kp is a pressure. Now, the pressure that is generated by most solids and liquids is essentially 1 bar, and that doesn't really change with temperature. So if the P over P naught is essentially 1 over 1, those terms would not change as the reaction progresses. And so they're going to have no effect on the Kp. Because they do not affect the pressure of the system, they are not, because the pressure will not change, they are not going to be considered. They cancel out. 1 over 1 cancels out. But also, finally, how did we convert Kp into Kc or anything like that? We can convert this through K key, which is our mole fraction. So we can convert this to a mole fraction or concentration, that because pressure at equilibrium is equal to the mole fraction times the pressure, or essentially the partial pressure of the thing is the mole fraction times the total pressure. So, and then we can factor out the total pressures all the way out to say, oh, if we wanted to say K of key, you got pressure, you got the total pressure raised to the power of how many moles of gas do you have. Doing the same thing. Well, concentration is moles over volume. And pressure, so pressure must equal concentration times RT. So, oh geez, what the heck is going on? So we're going to factor out, you turn C, the pressure into CRT. Now, in order to factor out, we have to factor out P naught. And in order to cancel out units, we're going to multiply everything by C naught over C naught. So that we get C over C naught. So the units of molarity and molarity cancel, molarity and molarity. RT over P. So molarity, so 1 molar, 1 bar, R and T, delta V. So all these things canceled out, and so we just the same thing, RT. We're just introducing a little bit more complexity to keep the units straight, but we didn't worry about that in general chemistry. That concludes this chapter. This was a difficult chapter, but it is something we really need to consider moving forward. So thank you for sitting in, listening to this, and hopefully this will help you as you progress through your studies. This is Chemistry Cowboy signing off.